Today's goal is to perform arithmetic operations on polynomials. And by arithmetic operations, we mean we're going to take polynomials and add them, subtract them, multiply, and possibly divide them. Let's get started on our first example. If we're evaluating, the directions themselves give you a clue. The word inside evaluate is value, which is a number. This is telling us your final answer should just be a number. F of 4 means we need to substitute 4 into the function every time where we see an x. So that will look like negative 3 times 4 squared plus 5 times 4 minus 1. PEMDAS, the order of operations, tells us we have to deal with the exponents before anything else. In this next term, we can go ahead and multiply. So we have negative 3 times 16 plus 20 minus 1, which is negative 48 plus 19. Which gives us negative 29. True to the directions, our answer is just a value or a number. In B, if we're asked to simplify 4x, this is a hint, right? Our answer isn't just going to be a value. If it's not just a number, it'll probably have variables in it. So this notation maybe looks weird, but essentially we're just substituting. But instead of substituting 4 into the function, we're substituting that entire expression for x. So this will look like negative 3 times 4x squared plus 5 times 4x minus 1 gives us negative 3 times. Again, we have to do the exponents first. So we're going to square the expression 4x. That means we're essentially doing 4x times 4x, which gives us 16x squared. Not just 16, but 16x squared plus 20x minus 1. Multiplying gives us negative 48x squared plus 20x minus 1, and there are no like terms to combine. Again, true to the directions, they didn't promise us our answer would be a value or a number, and it turns out that our answer had variables in it. Our answer is an expression. In C, if we're simplifying 4 times f of x, that means we're taking this entire expression f, and we're multiplying the full thing by 4. So this will look like 4 times, in brackets, or times the quantity, negative 3x squared plus 5x minus 1. We can now just distribute that 4 to each of the terms in the function f. So we get negative 12x squared plus 20x minus 4. Last one, express p of x equals f times g in standard form. So that means p, probably because this is a product, we have two functions that we're going to multiply. That's because they're sitting next to each other. Okay, let's find out what f and g are. Here's f, here's the function g. We're going to put them side by side and then go ahead and multiply them. So p of x equals, we have negative 3x squared plus 5x minus 1 times 2x minus 7. To multiply these terms, I'm going to draw myself a really big box and apply the box method. One column per term. And we get negative 6x cubed plus 10x squared minus 2x plus 6x squared minus 35x minus 7. Now I'm on the hunt for like terms. Ooh, I've got some x's I can combine. And I've got some x squareds I can combine. So combining my like terms, I have p of x. My product new function is negative 6x cubed plus 16x squared, and putting these in descending order of power of x so that my function is written in standard form. Okay, let's take a look at our second example today. Suppose the polynomial f has leading coefficient a and degree m. Well, g is a degree n polynomial with leading coefficient b. If m is greater than n, name the degree and leading coefficient of this new function, f plus g of x. Now this notation looks weird, but this is just saying we're making a new function by adding together the entire functions. Well, we don't know much about f, but we do know it has the form a x to the n, because here's its leading coefficient and n is its degree. So it's going to maybe have some other terms, like maybe it'll have, if n is 3, it's a cubic function. Maybe it has an x squared term, maybe it doesn't. Maybe it has an x term, maybe it doesn't. Maybe it has a constant, maybe it doesn't. But we do know that it has this one term. Now we're going to add it to the terms of g. Well, we only know one term of g. It's a degree m. Oops, there's a typo in the question, and I'm sorry about that. This is supposed to be a degree m function. Oops. It's a degree m function with leading coefficient b, so it looks like b times x to the m. Again, maybe m is 142, so it's a degree 142 function, and maybe there are 100th terms and x cubed terms and quartic terms and whatever. We just know it has that one term. So if we're going to put these in standard form, we got to know which one of these guys comes first, the ax to the n or the bx to the m. Well, here's our clue here. If m is bigger than n, this term has a higher power and a higher exponent than ax to the n. So if we put them in order, we have bx to the m plus, I don't know, maybe there are terms in between, maybe there aren't. Then we'll have that ax to the n term eventually, and maybe some more terms. We don't know much about this new function. We just know that the highest power of x, when we add these two functions together, is m. Well, that's our degree, right? We're asked to name the degree and name the leading coefficient. So the degree of this new function is m, and the leading coefficient is b. Okay, let's take a look at our next example. Oh, name the degree and leading coefficient of fg of x. Okay, well, this means we're taking f of x and g of x and multiplying them. The notation looks weird, but they're sitting next to each other, which means multiplication. So this time we have ax to the n plus maybe some other terms times bx to the m plus maybe some other terms. If we multiply them, let's look at an example off to the side. Like if we had 2x to the 5th plus a bunch of stuff times 3x to the 7th plus a bunch of stuff. If we multiplied these first two terms, you would get 6x to the 12th, right? X to the 5th means you're multiplying x by itself 5 times. X to the 7th means you're multiplying x by itself 7 times. So altogether, you're multiplying x by itself 12 times. So we see we took these coefficients and we multiplied them, the 2 times the 3. So over here, we'll get AB when we multiply these coefficients. And the exponents, you end up adding them, because this is telling you how many times you're multiplying x by itself. This tells you how many times you're multiplying x by itself. And so altogether, over here, we'll have x to the n plus m. Now, if we use the box method like we did in example 1, right, we had 3 terms times 2 terms, you end up with a giant box. If we multiply f and g, we may end up with a whole bunch of other terms, but this will be the term with the highest power of x. So it tells us the degree is n plus m, and the leading coefficient is ab. One more problem to look at today. What will be the degree and leading coefficient if we take the two functions and subtract them? We'll have ax to the n plus a bunch of other terms minus bx to the m plus possibly other terms. If we distribute the negative sign to the terms in g, we have ax to the n plus some other stuff minus bx to the m minus its other terms. And again, we know that m is the highest power. So we've got to put it first when we're rearranging to put the function in standard form. So we have some terms from g first, eventually some terms from f, and so that tells us that our degree is m. It didn't change when we just rearranged the terms, and our leading coefficient is negative b.